Okay. Okay. Recording started. So today let's continue the discussion on convex and smooth problems. The last time we talked about how to solve the strongly convex and smooth problems using gradient descent and the convergence guarantee. Okay, basically for strongly convex and smooth problems, the function has a lower bound and upper bound. Okay, in the following sense, either is if we consider second order derivative or the Hessian matrix, it has its minimum eigenvalue, and the largest eigenvalue has this lower and upper bounds. Right. But in many cases, and we have this geometric convergence rate. Okay. But in many cases, the strongly convex condition may not hold. For example, in the homework, when we consider this least square problems, we have shown that the second order derivative matrix is basically A transpose A. Okay, and in many cases, this matrix A, let's say, is M by N, and this X is N by 1, right? And this B is M by 1, so that these dimensions are compatible. Now, in many cases, X, let's say X has dimension N. For this A, in many practical applications, the number of rows is far less than the number of columns. Okay. If you think about this N, this number is the dimension of the unknown variable. So we are solving this equation well, the unknown variables has dimension N. So this vector X has dimension N. But in practice, the number of rows is M is far less than N. So we have in many cases we only have a few number of measurements or a few number of linear equations. And the consequence is that this second order derivative, A transpose A, you can check this, the dimension of this one is N by M. Okay, because A transpose is N by M. So after multiplication is N by N. So if I can visualize this one. This A basically in many cases is a flat matrix. Okay, and A transpose is a high matrix. It's a tall matrix. And after matrix multiplication is a big matrix. Now, the issue is that for this matrix, the rank is deficient. So the rank is smaller than N, which means that the minimum singular value is 0. Okay, so we can only say this matrix is positive semi-definite. But the minimum singular value might be is 0 in this case. So it is not strongly convex. Not strongly convex. So for this least square problem, it does not fall into the strongly convex class. Okay. Therefore, this motivates us to consider further consider this class of problems where we do not have strong convexity. We only have convexity and smooth problems. And in this case, such a least square problem fall into this class. It is convex because the Hessian is positive semi-definite. Right? It's bigger than or equal to 0. It's positive semi-definite. So it's convex, but not strongly convex. It is smooth because this Hessian matrix, it always has an upper bound. It always has a largest, the largest singular value is always finite. So it is smooth. Okay. And the question is, for such a class of problems, what is the performance guarantee of gradient descent? Can we still achieve the geometric convergence rate as what we have shown for strongly convex problems? Okay, so this is a setup. We consider minimize a function where f is only convex and smooth. And the last time we discussed that the idea algorithm design is that for this class of problems, we can easily construct some convex examples. Well, the sequence may go to infinity, but the function value still converges. So maybe we should consider function value in this case instead of considering the distance to the minimizer. Right? In this case, we don't have any minimizer. And the key idea to the analysis is that we want to develop a simple majorizing function that majorizes the function, objective function fx. And we will explain this very soon. So from the smoothness assumption, we know that this inequality holds. Okay, let's look at the first inequality. Because function f is assumed to be smooth. And last time we have discussed that as for smooth functions, we have many equivalent conditions, right? A function is smooth, convex function is smooth if the following conditions holds, right? They are equivalent. So especially the first one holds, right? The first one is frequently used. It says that if you pick any 2 points, x and y, this inequality holds. Okay, the left-hand side is at 1 point, the right-hand side is a first-order Taylor expansion plus a quadratic term. Okay. So this holds for any x and y. Therefore, I simply set y to be x plus 1 and x to be xt. Well, xt and xt plus 1 are generated by gradient descent. Okay, but this inequality, okay, holds for any arbitrary 2 points. So I specify those 2 points. It still holds. Okay, so the first one is smoothness. Now the second line is an equality. Well, we leverage the update rule of gradient descent. Remember, gradient descent says that xt plus 1 minus xt is what? It's negative eta t gradient fxt. This is a gradient descent update rule. The increment is the negative gradient multiplied by a step size eta. So you plug this increment into this the right hand side. This guy becomes this negative gradient thing. And because it is a negative gradient, so here's a gradient inner product with a negative gradient. So we end up with negative eta t times the norm, the L2 norm to the power of 2. Okay, it's the inner product with itself. So that just becomes the norm square. And the last term is just this term to the power of 2. Okay, taking the L2 norm to the power of 2. And the eta t is a scalar, so we can pull it out. That becomes eta t squared. Okay. Plug in the update rule of gradient descent. And then you can see these two terms can be combined together because they are all about gradient norm to the power of 2. In particular, we can see that these two terms, one is negative, one is positive. So we can pick a proper step size to minimize these two terms. Okay. So in particular, we can choose eta t to be 1 over L, so that these two terms, they are actually sort of match with each other. In the end, they can cancel out and becomes a negative term. Okay, so you plug in this choice of step size, and these two terms can be combined together into the following term. It's negative 1 over 2L multiplied by the gradient norm to the power of 2. Okay. This shows that this is a very interesting result. So this shows that this can be summarized into the following result, right? If a function is L smooth, and suppose we apply gradient descent with such a step size, then we can show that the function value satisfies this inequality. Well, this inequality says that the next step, the function value at the next step, is less than the previous function value. The function value at previous step minus some positive terms. So this actually implies that this sequence, the function value sequence, right, is decreasing. So this implies that fxt is a decreasing sequence, which is desired because we want to do minimization, right? We want to minimize the function value. So it is desired that the function value is going down. And you can see the progress is more or less controlled by this term, the last term, right? It depends on the gradient norm, the norm of the gradient at your previous step t. Yeah, if you have a relatively large gradient at the previous step, then the progress will be bigger. Right, so this is a very small and elegant result. And you see that to prove this result, we only utilize two conditions. One is that we assume the function is smooth, L smooth. The second thing is that we apply gradient descent with such a step size. Okay. We don't even need convexity to prove this result. Okay, this result does not need convexity. It holds for any smooth functions. Okay, so this is a good sign. It implies that gradient descent makes sense, right? Because it always generates a decreasing. It always decreases your objective function value if you choose the step size in a proper way. Okay, so you can see the step size is actually related to the parameter of your function's smoothness. If this L is bigger, then you want to choose a smaller step size and to be more conservative. Okay, so this is about function value decrease, and it is natural to ask if the variable also decrease decreases the distance toward the minimizer. Okay, so another question is, if this variable xt, the distance between the variable xt and the minimizer s star is also decreasing. Okay, we have, but in the previous slide, we have function value decreasing, but it will be better if we can further show this distance decreasing. And if the function is strongly convex, we have shown this. We have actually shown that the variable distance decreases at a geometric rate. But here, we cannot show that fast convergence. But instead, we can just show this diminishing distance result. Okay. So let's consider this one. We can prove the following fact, which we will prove right next. If the function is a convex and L smooth, and if we pick such a step size, then the distance to the minimizer, okay, the distance to the power of 2, this term is diminishing in this sense. Right? This is xt plus 1 minus x star. L2 distance to the power of 2. Compare with the last distance term. Right? This is the xt minus x star. It is bounded by the previous distance minus such a positive term. Okay. So in this sense, the distance is decreasing. It's decreasing. Well, this x star is any minimizer of f. This can be any minimizer of the objective function. So this proves, this fact, this small result shows that the distance is diminishing if the function is convex and smooth. Right. And we pick this step size. If you compare this result with the previous one, you can see that their assumptions are different. The previous one is more flexible because it only requires function to be smooth. Right? Function may not necessarily be convex, but this condition we require the function to be convex in addition. And the proof of this result is not that straightforward. So let's consider the proof. Again, we start from t plus 1 and it goes to time t. And by the update rule, we know xt plus 1 is xt minus the gradient, well, times the step size. And here I introduce this term again because this is a gradient at the minimizer, so it's just 0. Okay. So the first step is just plug in the update rule. And then in the second step, I'm going to expand this quadratic term. This is a distance to the power of 2. I can expand it, just expanding quadratic terms of scalars. So I view this as one term and this as a second term, and I just expand it. So I will have the first term to the power of 2, okay, and this is the second term to the power of 2, and then in the middle I have the intermediate cross terms. So it's minus 2 times the dot product of these two terms. Okay, it's just the expansion. And for the second term, for this inner product term, this term is about xt minus x star inner product with their difference in the gradients. And we have shown in the previous lectures that for convex and the smooth functions. So let's go back to this one. Right. For convex and smooth functions, this inner product can be controlled in various ways. This is one of the ways that that we can control it. F is convex and smooth this inner product for any x and y. This inner product term is lower bounded by such a quadratic term, right? It's the distance, L2 distance of the gradients to the power of 2. So we use this result. And remember that this inequality is a lower bound. It's greater than or equal to. Okay. And now we just directly apply this result. And because of this negative sign, okay, so this inner product term, by utilizing that result, is greater than or equal to 1 over L times this distance term. Okay. And because of the negative sign in front, so this is greater than equal to, but because of this negative sign, this becomes less than equal to. Okay. So we can get the third line is less than equal to the distance, L2 distance to the power of 2. Okay, and then this, so basically we upper bound this this dot product term using the norm of the gradient. And then the last two terms can be combined together they can be combined together, and also plug in the choice of step size. You can simplify that into the last term. Okay. And then finally, this is basically 0. This is 0 because it's a gradient that minimizes. So this proves that claim. Right? The distance at t plus 1 is, see, there's one inequality along the way. So overall, it's less than or equal to. Distance at t plus 1 is less than or equal to the distance at time t. Subtract this term. So this proves this result, right? And we need both convex and smooth, because this bound, right, when we prove this bound in the last lecture, we utilize convexity and smoothness. So this inequality only holds for convex and smooth functions. So this means that for such a class of function, this dot product term can be roughly controlled at the same level as the distance term. This is a very, very nice geometry. Very nice of geometry. If you pick a random function, this dot product term can be is in general very hard to control. So we have these two results, right? Let's recall these two results. One is that function is decreasing, function value decreasing. Okay. This one, distance decreasing. And combine these two, we can further show this main theorem. This is the main convergence guarantee for gradient descent. Okay. Let's look at this one. Let f be a convex and L smooth function. Okay, any function in such a class of convex and smooth function. If we pick step size, if we apply gradient descent with step size 1 over L, then we can have the following bound. Function value at xt. The function value at time t minus the optimal function value X star is the minimizer. So minus the optimal function value is bounded by such a term. The right-hand side is 2L times the initial distance to the power of 2 divided by t. And you can see the numerator is just a constant. It's constant, depends on L, depends on the initial distance. But the denominator depends on time. The number of iterations you run for this algorithm. Okay. If you run it for 100 times, then t is 100. So this is a rough estimate of this is called the convergence rate of the function value. But this rate shows that the function value is decreasing at roughly 1 over t, at roughly the rate 1 over t. Okay. So fxt minus fx star, right, roughly is 1 over t. Roughly 1 over t. And again, we can discuss the iteration complexity if we want to achieve an epsilon accuracy. Then I require t to be what? To be bigger than roughly 1 over epsilon. Right, just the inverse of the other one. Okay. So this is the iteration complexity of gradient descent when applied to solve convex and smooth functions. And we can compare this one with the iteration complexity of gradient descent when applied for strongly convex and smooth functions. In the previous lectures, we have shown that for strongly convex problems, the iteration complexity is just big O log 1 over epsilon. Right? Whereas for convex problems, it's 1 over epsilon. So if you compare these two, obviously this one is much smaller compared with 1 over epsilon. Okay. You can O is like ignoring all the constant terms, right? Like ignoring all these constant terms. Yeah. So it's some constant times this log 1 over epsilon. Yeah. So basically, in some cases, we use big O notation to simplify the result, so we can focus on these critical terms. Right? Because here we only focus on how many iterations we run, or how much accuracy we want to achieve. The other constant terms, they do not affect too much. Yeah, because of this log, the difference in the complexity is huge. Yeah, if epsilon is 10 to the negative 10, then this one, right, if we solve a convex problem, we may need to run 10 to the power of 10 iterations. But if we solve a strongly convex problem, we will take a log, so it's 10 log 10. That's a much smaller iteration complexity. Okay. So this rate is a much slower convergence rate. It's a sublinear convergence rate. This is because sublinear. Well, the previous geometric convergence rate for strongly convex problems, we call that linear convergence. So this is sublinear. Sub means it's kind of slower compared to linear. And here we want to, so next is to let's prove this result by utilizing the previous two results. And here the proofs is a bit. So let's go over these steps one by one. We have shown this in the first result. The function value is decreasing along the iterations. Now the big picture is that we want to get a bound on the function value, right? Because this is what we want to control. So in order to do that, we can start from this step, but we need to further control this gradient term in a certain way. Right? And the idea is that we want to control this term with using some terms based on function values. Okay. Then we can have a kind of have a recursion on this on both sides, and then we can do that iteratively. So we can show this result. Okay. So first of all, using convexity. This is the definition of convexity. For n in 2 points, this inequality holds. Okay. This is a definition of convex functions. But I specifically choose the first point to be x star, the second point to be xt. And then this is an inner product term. Inner product term, we can utilize the Cauchy-Schwarz inequality. So the inner product between two vectors is bigger than or equal to the negative of the product of the norm of these two vectors. Okay. The second is a Cauchy-Schwarz inequality. Now, solve this inequality for this gradient term. We can get this result. Okay. Let's rearrange the terms. We get a lower bound for the gradient, for the norm of the gradient. Okay. And you can see this inequality connects the gradient of your function at time t to the to the distance or to the gap to the minimizer, right? On the left hand side we have gradient. On the right hand side we have something related to the distance or the gap between xt and x star. Okay. So you can imagine if xt is far away from x star, maybe the gradient will be bigger. So the right hand side will be kind of bigger. And then in the denominator, because we have shown that the distance is decreasing for this term, right? The gradient descent for this algorithm, the distance will be decreasing, which is the second result we just showed. And so we can replace that because it is in the denominator. We can replace that with a bigger number, right? So this distance in the initialization iteration is bigger, but it's in the denominator. So it's actually this is greater than or equal to. This is a smaller term. Right. Then we want to do this because we kind of want to fix the denominator as a constant, so that we can iteratively solve this inequality. Right. Now what we do is to plug this inequality back into the first one. Okay. Plug this into this one, and you can see it is consistent because this is less than or equal to, but we have a negative sign here, while this one is greater than or equal to, right? If you multiply by a negative sign, it will be less than or equal to. So it is consistent. You can plug it into the above one. Okay. And so plug this one into this one, and then introduce this notation to simplify the notation. Okay. Delta t is fxt minus fx star. Okay, define this notation. Then this difference is basically delta t plus 1 minus delta t. And the left hand side is just that one. And the right hand side, well, you just plug this one. You will see this is this is gradient to the power of 2. So you raise both sides to the power of 2. You will have delta t to the power of 2 divided by distance to the power of 2. Right? And the other one is constant, this constant coefficient, and a negative sign. Okay, just plug it in. And the denominator is a constant. I just write it as omega 0, just constant. Okay. So this defines a recursion. Well, delta t is what we want to bound. We want to bound this term. And this is a recursion of delta t. Left hand side is delta t plus 1 minus delta t. Right hand side is delta t squared, negative delta t squared. So the rest of things is just pure mathematics. You just solve this recursion of the scalar sequence and try to get an estimate for this for delta t. Okay, so let's copy the recursion here. What we do is this: divide both sides by this product. I can do that because the product is positive. Delta t is always positive, right? Recall, delta t is always positive because it is we are subtracting the minimum value. After that, okay, so if you do that and rearrange the terms, I think this term, right, once you divide it by this one, is 1 over delta t. It is here, and this term is here. Okay, and this term becomes this one. Okay, so you just rearrange the terms. And then this ratio can be further simplified because delta t is bigger than delta t plus 1. Right, we have shown that this inequality, this function value is decreasing, which means your delta t is decreasing. Delta t is decreasing. Okay. And delta t is decreasing, so this is bigger than 1. This one is bigger than 1, so it will be bigger than or equal to 1. Okay, you can replace this by 1. This is greater than or equal to. Doing that, we get a simpler recursion. Okay, simpler recursion. Now this is a very simple recursion, but you can just unroll this one over the iterations. Just unroll it t times, you can get this estimate. Okay. You can get this one. And you can further ignore this one. It's a constant, doesn't really affect the. So it's lower bounded by t times t divided by a constant omega 0. And then you solve for delta t. So delta t is less than or equal to omega 0 over t. Well, this omega 0 is the constant we just defined. Okay. So this proves the final result. We get an estimate for the function value gap. So you see the key is to establish this recursion, based on the small results that we have proved. One is function value decreasing, one is a distance decreasing. Okay. So this is everything about convex and smooth problems. So we can see for this type of problems, this is a bigger class of functions. It includes the class of strongly convex functions. So it's a bigger class. That's why the algorithm may have a worse performance. So the convergence rate, function value convergence rate is 1 over t, a very, very classic result, 1 over t. And next, we further consider a non-convex problems. So we further drop the convex condition, right? So we just consider convex and the smooth problems. But now let's just consider smooth. We further drop the convexity. Function may not be convex. So for this class of problems, we usually call it the non-convex and the smooth. Non-convex means that it is not convex, so it's complementary to the convex case. So we call this the non-convex problems. And the non-convex problems is everywhere in practice, especially in machine learning and many other signal processing problems. For example, the famous deep neural networks, it is highly non-convex in the high-dimensional space. So for these problems, they are not even convex. Okay. And the landscape of the function of a non-convex function may look like this. Basically, you will see a lot of local minimums and local maximums, and that makes the optimization very challenging. Right? For convex problems, you kind of have only one local minimum. For convex problems, every local minimum is a global minimum. But for non-convex problems, it could be very complex. And there are some negative results to say that no algorithm can, in general, we cannot design algorithms to solve non-convex problems efficiently. Okay, it's called NP hard problem. But for smooth problems, we can do something to it. Okay. So for non-convex problems, we need to change. We need to reconsider our convergence metric, because we no longer have there might be many local minimums. We may end up converge at a local minimum. So we will change our convergence criterion to be the so-called stationary points. We look for points where gradient are 0. And you can imagine from this figure that both local minimum and the global minimum points, they will have 0 gradient, right? So this is a very weak convergence metric. Okay, but this is kind of the only thing we can do in this case, because this is such a very complicated problem. So it is in reality, we may end up converge to local minimum. Okay, so here we'll set up our convergence criterion to be stationary points. Okay, this means that the goal of the algorithm is to find a point such that the gradient is very small. Okay, the gradient is very close to 0. So we call this epsilon approximate stationary point. So you are epsilon away from 0. And the question is, how fast can gradient descent find such a point? The result is very, actually turns out to be very simple. So for any smooth functions, it may not be convex, it could be non-convex. For any smooth functions, if we choose step size 1 over L, then we can have this control. Okay, the minimum gradient among all the iterations is bounded by roughly square root of 1 over t. If you look at the right hand side, square root of 1 over t. This is a constant. If f is convex, then we have this improved result. But I think here I will just talk about this the first result, because the first result is just about smooth problems, right? Smooth and general non-convex problems. And again, if you want to achieve, so from this result, if you want to achieve epsilon accuracy, right, you set this to be epsilon, you solve for t, you can see that t will be roughly 1 over epsilon squared because of the square root. So this is the complexity of gradient descent for solving this class of problems. And the proof is actually very simple, because now we no longer have convexity, so we only have a very limited tool. We can only utilize the first fact. That is, the function value is decreasing. The proof of this fact does not rely on convexity, so it only relies on smoothness. So this holds for general smooth problems. And the idea is that we start from this inequality that we proved in effect. We just do a telescope sum over the iterations. Okay? Sum this inequality over k. On the left-hand side, it becomes a summation. On the right-hand side, the sum of difference, sum over difference, which will cancel out the intermediate terms. Okay? So you only have the starting point and the end point. Okay, you sum over t 0 to t minus 1, but you only have the 2 end points. And then, yeah, the left-hand side can be lower bounded by the minimum. Yeah, maybe I can write it here. So this sum is bigger than or equal to a sum. This is a sum of t minus 1 minus t0 terms. It's bigger than equal to the minimum among these terms multiplied by roughly t minus t0. We have this many terms. If we consider the minimum, a very simple estimate. Sum of say you are summing over 10 positive terms, it is bigger than equal to 10 times the minimum. Right. So that's how we get this minimum one. And then you just move this constant to the right-hand side, and here's a square. So you take square root, right? You can get this one. Right? These are the constants. So it's this one, and the rest 2L, and this one are the constants from the left-hand side. and you take square root. Okay, you can get this. You can get this bound. But I think you just set t0 to be 0. Okay, you just start from 0. Then you have the first claim. Then you have first claim. So the proof is actually very straightforward. Just do a test coding sum and then the result is obtained directly. Yeah, and this is also intuitive because your function is decreasing, right? And it's decreasing, and the progress is bounded by gradient norm. So once you reach a local minimum or a global minimum, your gradient will be very close to 0. So there must be some upper bound that you can control over the gradient. And here we just need to sum them up and consider the big picture. Yeah, you see, once you sum them up, the left-hand side, if you keep summing this over the iterations, the left-hand side you have more and more terms, right? You are summing over, and you can have infinite number of terms on the left-hand side. But the right-hand side, if you take a look at the right-hand side, it is, if you back to 0, let's say if you choose this one to be 0, then it is bounded by what? It is always fx0 minus fx star. It's always a constant. The right-hand side is always a positive constant. But the left-hand side is a summation over infinite terms. Summation over infinite terms bounded by a positive constant. It means that your left-hand side, well, once you go to infinity, the gradient must be very, very small. Otherwise, those infinite sum cannot be controlled by a constant. So this is the intuition. The function progress, like the overall progress you can make on the function value is bounded. Yeah, and you can take a look at the second result of for convex. If we further have a convex, if the function is convex, okay, then this result, this rate can be improved from square root of 1 over t to 1 over t. This is an improvement. And yeah, so I will skip the proof for this part, which is also very simple. Yeah, so this finishes the lecture 2 or lecture 1 actually, and then let's just look at the homework problems. So we're looking at homework 2. Yeah, so you need to write a code to implement implement this algorithm to solve this problem. And this file describes how you can set up your problem. Okay, so this is the least square problem that we are looking at. Okay, well, x, a, and b here I specify their dimensions, and this is how you compute the gradient. Okay, this is the given formula, the gradient formula. So what you do now, given this formula, you can implement gradient descent. What you do is just following this gradient formula and following the rule, update rule of gradient descent. It's just a matrix vector multiplication. You can implement it using either MATLAB or Python. But and then let's generate this all this data. So here we need to generate A and B more specifically. So this is how we generate this model. We first need an underlying signal Z. This is kind of the underlying ground truth for X. Okay. And then we need to generate a measurement matrix A and observations B using the linear model introduced in the class. And the following are specific steps. The first one is you can pick, you should determine the dimension and the number of measurements. It's basically N and M. You can choose any number you want. Now, typically, the N could be 100, for example. The measurement could be 500 to 1000, for example, but you can choose any number you want. And generate your underlying signal Z in any way you want. And Z must be a vector of Rn. Could be, you can generate it using a random distribution or just create any signal you want. And then the third step is to generate this measurement matrix. What we do is to generate a set of Gaussian measurement vectors. Well, this AI, you can imagine AI is the ith row of matrix A. And basically here, all the entries of AI are generated IID from the standard normal distribution. Okay, so you can do this using either MATLAB or Python. They have commands. Well, you can generate a matrix or vectors of Gaussian random numbers. Okay, you can just check Google. Right. Basically, you generate a matrix A where all the entries are following the standard Gaussian distribution. Okay, check MATLAB or Python. After that, you have the matrix, you have that random matrix. You normalize the vectors to have a unit L2 norm. Okay. For each row, you normalize it to have a unit norm. This is to help. This may improve the numerical stability sometimes. Sometimes if you happen to get a big number, random number, that could cause some divergence issues. So here, just normalize the rows to have a unit norm. I think MATLAB and Python also has those commands, or you can just do it manually. Okay, for each row, you compute L2 norm, and for that vector divided by this L2 norm. Okay, and then you will generate this vector B. Vector B is called your observations. This is generated using the following linear model. Well, BI is an ith observation. This is generated by AI transpose Z. So it's AI transpose Z is like I'm using the ith measurement vector to interact with my underlying signal Z. Okay, and this should be my underlying true observation. But then this observation is corrupted by a noise, delta I. But delta I is a Gaussian noise. So you generate a delta I randomly and use that noise to corrupt this observation. The corrupted signal is the corrupted result is your BI. Okay. And you can choose the variance, pick a variance that you like. After all this, we have matrix A, your measurement matrix. We have the noisy observations vector B, right? And given A and B, that problem is well defined. The least square problem is well defined. Okay, so up to this step, you have created your own least square problem. And then you just follow these instructions to implement this gradient descent algorithm. Okay, pick a proper learning rate and the initialization. Anything could work, I think. The learning rate, you probably want to try, you can try different learning rates and see if you can tune one that works the best for for your own experiment. Right, you start from some initialization, you implement this algorithm iteratively. The algorithm will generate a sequence of variables xk. Now, what you need to report is the following. The first one is the training loss curve, which is the fxk. Now, for each xk you obtain, you can calculate this objective function value, right? And then you have a function value over iterations. You can plot the loss curve, training loss curve. And the second thing you can report is the estimation error curve. It's like for each xk, how far it is away from the underlying true signal z. It's xk minus z divided by the norm of z. This is a relative error. Okay, so these are the two curves that you need to report. And then also, you need to explore the impact of the following parameters on the estimation error. So this error critically depends on many stuff, like what is how much noise you add to the observations, right? So here, you can change the parameters, the following parameters, redo the experiment, right? And see how that affects this estimation error. So you will change your measurement dimension ratio. But you can fix the dimension and then vary the number of measurements. See how does that affect the estimation error. Now, intuitively, right, if you have more measurements, you have more data, you are expected to get a better estimation. Right, this is one thing. The second thing is the noise variance, sigma square. If your noise level is bigger, so the data is more corrupted, estimation error will be higher. Right? That is expected. And also the learning rate. Yeah. So right after you write this code, you just need to tune those parameters. Right? Just to change those parameters, rerun the code, should be a simple stuff. Yeah. Yeah, and in your submission, right, you can tell me like how you specify this like this delta, this noise, what initialization you choose, what is your learning rate, specify those parameters, and then show me these figures, right? So make everything explicit and self-contained. Okay, so this is a very simple least square problem, a quadratic least square problem. Okay, any questions about this homework setup?
When's it due?
Yeah, I will give you about one week. Yeah, so I will set up a deadline. About 1 week, 7 to 10 days. Okay.
All right. Can you explain why you would set the step size to 1/L?
Yeah. Yeah, this is a very critical choice, because the intuition is that when we derive this result, so we end up with this bound. And this is a quadratic function in the step size. Right? If you view the other terms as constant, this is negative eta t plus eta t squared. It's a quadratic function. So you want to what? You want to maximize, you want to minimize the right-hand side so that you achieve the maximum progress. Right. So you just do a simple, you simply optimize the scalar, and you will see 1 over L is the best choice. Right.
Minimizing the left side, which is the top line, right?
No, the right-hand side, right, is quadratic in eta. So you can optimize this simple quadratic. This is a quadratic optimization over a scalar variable. And you can see that 1 over L is the best choice. Right. We pick this step size to minimize the right-hand side, to minimize the majorizing function. Like this will tighten this inequality because it's less than or equal to the right-hand side for any positive eta. So you can choose the one that minimizes this upper bound. That is the tightest estimate you can get. And turns out that 1 over L is the tightest estimate you can get. Yeah.
All right.
This also connects to the problem itself, because L stands for the maximum singular value of your of the Hessian matrix of your objective function. If the function has a very large singular value, then you have to be conservative in the step size, because that simply means along certain directions, the function is growing very, like the landscape is relatively flat. So you want to move, I think it's relatively sharp. So you want to move very slowly to avoid divergence. So this is a geometric parameter.
So if L is large, then the function is sharp. So you would want to pick the small step size.
Yeah, if L is large, like this inequality, the right-hand side is controlled by a very big quadratic term. So you want to be conservative when you choose the step size. Yeah, and maybe we can have a quick start of the lecture 2. We have 10 minutes left. So lecture 2 is about, again, we focus on gradient methods, but now we are looking at the more challenging type of problems. Well, these problems has constraints. Right? In lecture 1, we talk about minimizing different classes of problems, but the minimization is over the entire space. There's no constraint in your variable. But in many cases, right, the problems we consider, they have constraints. So here, in this, we will basically talk about 2 different algorithms. Frank-Wolf and the projective gradient methods. But before that, right, the problem now we consider is minimize fx subject to a certain constraint. This constraint is C is a convex set. This f is a convex function. C is a closed convex set. For example, the constraint could be, in many cases that we have seen, they could correspond to in the sets defined by linear inequalities. We have linear inequality constraints. Yeah, but I think we'll see some examples later. But it could be more general than just linear inequalities. And the key idea is that since now we have a constraint, right? If we don't have any constraint, we just do gradient descent, compute the negative gradient, apply the update, and then we are good. But the problem here is that if we follow gradient descent, after the update, after we update the variable, it may go out of this constraint, right? So there's no, like gradient descent has no control over the right. Suppose this is the feasibility set C. We call this the feasibility set. We only consider, like, the optimization problem is only considered within this set. We are restricting the function within this set. But if you follow gradient descent, it is possible you may jump out of this feasibility set that violates the constraint. So we have to fix this. We have to fix this one. So the idea is that instead of looking at negative gradient, if you just follow negative gradient, you may go out of this, you may violate this feasibility set. Instead of doing that, we still consider the same update rule as gradient descent. Right? It's just every time you apply a step size multiplied by some updates dt. But in gradient descent, dt is the negative gradient. But here, we will restrict dt to be a feasible direction so that after we apply this update, xt plus 1 will be still contained in the feasibility set. Okay, so we put a restriction on dt. Now the question is, how can we find a good feasible direction? And we call this feasible direction, meaning that once you apply this update along dt, the updated variable will still be inside C. That you are searching within these constraints. But the question is, how can we find this dt? How can we find a good dt for a specific type of constraint optimization problem? The question is, can we guarantee this feasibility while enforcing cost improvement? Right? Can we guarantee this while still choose a good feasible update direction dt? Yeah, and I have 5 minutes. So the first algorithm we will discuss is the very famous algorithm called Frank-Wolf algorithm. This algorithm has a very simple. It's very simple. The update rule has 2 steps. the first step is to solve a very simple constraint linear program. It's a linear programming problem. If you look at this optimization problem, we are optimizing this linear function. It's an inner product between your gradient, your current gradient with x. Right? This is a linear function in x. Okay, so you optimize this, you minimize this linear function over your constraint set. Right? This is your objective linear objective function, and you are minimizing it over the constraint set. Okay. Now you assign the minimizer. Now this arc min, this notation, right? This notation means that the minimizer of this objective function over the constraint set. You find any minimizer, you solve this problem, find an arbitrary minimizer. You set that minimizer to be YT. Once you have that, then you update XT plus 1 as follows. The second step is very simple, it's just the interpolation between XT and YT. So the key is to solve the second line. So is to solve the linear programming problem in the second line. And here in this algorithm design, right, it does not specify, it does not tell you how to solve that problem, because it depends on what objective function you are dealing with. Right? It depends on this term, depends on the specific constraint that you are dealing with. So in practice, you have to work out this part by yourself. Right? But we will see many examples that this actually gives a very simple update rule. And the intuition, now, if you look at this algorithm design, the most important step is the second step. The last step is just a simple interpolation update. Now, the second step is, to explain the second step, we can consider the following equivalent update rule. Well, we add this constant offset, doesn't really change this optimization problem because this is just constant. And from this figure, we can see that, let's say this is xt, and this is the gradient direction, okay? Now, what we're doing is that, and this is the constraint C, the shaded area. Okay, this area is constraint C. So what we are doing here is that we are looking for a direction where x minus xt is like you are searching, you fix xt and you are searching over this shaded area so that this direction has the largest angle with your gradient, right? Because you want to minimize this in dot product. So you can see right, for example, this direction will be better than this direction, right? Because the angles, the inner product will be smaller. Okay. Right, so C constrains your search space. So we are still kind of following the gradient. So gradient is like a reference direction that we are looking at. We want to search for a direction X so that now this update is mostly negatively correlated with the gradient. So you can interpret this as following, we are trying to follow the negative gradient, but constraint within such a constraint set C. Because intuitively, if there's no constraint, imagine if there's no constraint, then the best choice maybe it's just a negative gradient. Like if you consider a normalized case, maybe the best vector is just a negative gradient itself because they are mostly negatively correlated. But now if we constrain this within a set C, it may not the negative gradient may not be contained in it. So it really depends on the form of this constraint. Yeah. So next time we will see that many classic linear algebra problems, again talking about eigenvalues of matrices, they are related to this type of constraint optimization framework. For example, the eigenvalue of a matrix can be formulated as such an optimization problem. It's a non-convex problem. Okay, so I think we can, yeah, we can stop here. You can take a look at this algorithm. It's actually very simple. So the only thing that we need to figure out is how to implement the second line, okay, in practice. All right. Okay. Thank you, guys. I will see you on Thursday.
Thank you.